Cool. So hello everyone. It's our pleasure today to have like Fangjun over here to share about this research work. And in this work, basically he developed some theory for us to analyze like quantum reservoir computing, and I think it's very interesting for us to understand and get him present about the work so that we can kind of use the theory for our research and things. And Fangjun, the floor is yours. You can just like start.
Yeah, sure. Okay, hello everyone, and thanks Bingyi for introducing me. Today I will introduce my recent work just published 1 month ago. This work is collaborated with IBM Quantum Company and the Raytheon Debian Technologies Company. It is about you can see the title. It's about the quantum machine learning in the noisy intermediate scale quantum era. You may heard the name of the well-known NISQRC era proposed by John Princeton. So specifically in this work, we succeed in design a particular quantum machine learning architecture called NISQRC, which I will introduce in detail in this talk. It is some modified version of the design based on an existing quantum machine learning scheme called quantum reservoir computing, or QRC for short. And this research aims to answer one particular question in near-term quantum machine learning applications. As you may know, in modern machine learning, the inputs like the images or sentences, they lie in a very, very high dimensional spaces, and the input usually have just, it's just indefinite length. Then therefore they're so long that embedding them in the quantum system already requires a very, very deep quantum circuits. So when the time for encoding and processing is far longer than the computer's coherence time, you will lose all information by the time you measure it. So our primary question is that even if we don't have a perfect fault-tolerant quantum computer yet, like the IBM superconducting platform, whether the quantum machine learning algorithm can maintain the memory persistency of a quantum computer when we need to retrieve information from the computer. So let me first introduce some background knowledge about the quantum machine learning and quantum reservoir computing, because I think most of the audience maybe that's the first time for you to hear about this terminology. So let me start with the general idea of the supervised learning of classical inputs with parametric quantum circuits. Okay, so to understand the exact problems we are facing with and the solutions I can provide, let me introduce let's introduce the architecture of a general parametric quantum circuits. So the supervised quantum machine learning mentioned in this talk always concern the classical inputs instead of some quantum inputs, and it has three components: the classical input U, a quantum system curly U, and a desired target value Y star. So first, the input is represented by some high-dimensional vector U, and a collection of different inputs constitute the training and the testing data set. So for example, suppose you have a data set for images of cats and dogs, and now given the images selected from this data set, we want to classify a this given image. Okay, so now we can feed the individual input into a parameterized quantum circuits. This circuit depends not only on the input value U, but also some internal parameters inside the quantum systems. So for example, if you're using a quantum circuit to encode it, then the rotational angles inside the circuits are the zetas. Or if you use some Hamiltonians to encode the information of U, then, for example, the Ising type model, then the couplings and the drives in such quantum spin network forms this internal parameter zeta. Then we can access the information by taking by performing a POVM measurement of these systems. And I think in this talk, usually I just focus on the computational basis measurement. So it's just, for example, that if you have error qubits, then you do the computational measurement. It gives you, error bit strings. Then you have, 2 to the error possible outcomes, which is obtained from this quantum system. Okay, now we get these histograms after we measured it. Then the histograms of those outcomes are called features of this parametric quantum circuit. And finally, we use Y, which is a linear combination of the features X, to approximate the desired the desired target value Y star. So I mean, however, such approximation does not always succeed because now we are using a very general zetas here. So you may likely, misclassify these images in your output. So that's why usually we need loss functions, L of Y and Y star, to quantify the performance of the approximation, whether Y and Y star is close enough or not. So usually for a continuous problem, that should be, mean square errors. And if it's classification problem, this error usually chosen as like a cross entropy loss. Okay. Then, it requires us to train this internal parameter theta by using the gradient descent. You can compute this gradient with respect to internal parameter thetas and gives you this gradient and use this information to update the internal parameters. However, it is well known that computing such gradients in the quantum machine learning is extremely difficult because of the complexity of quantum dynamics. So a worse phenomenon occurs if one increases the number of qubits. You may have heard about this terminology. It's called the barren plateaus. It says that once your circuit encoding forms some property called quantum 2 design, then the loss function will have a landscape whose gradient covariance vanishes exponentially. So you can see that when you increase the number of qubits, most of the domain of the theta, the landscape of the loss function is quite flat. So it's very, very hard to train the parametric quantum circuits. It means that we may need a very huge amount of measurement shots or state of copies to train the parameter thetas, which is very, I would say completely infeasible in the near-term devices in the NISQRC era. The one scheme to avoid such difficulty is a solution called quantum reservoir computing. It is inspired by the classical recurrent neural networks and kernel methods. It says that we don't need to train the complicated internal parameters, and instead we'll just only train the output weights such that it minimizes this loss function given by this internal parameter, this output features. So for the parameters, we just need to randomly draw those thetas and keep them fixed. Then we just train these Ws in the final layers. Then you can argue that, okay, now we only train the W, maybe your expressive ability can decrease because now you lose the degrees of freedom to play with those internal parameters. But then as a compensation, we can use a much larger Hilbert space by increasing, for example, the number of qubits to compensate for it. Okay. So since usually, as I said, this loss function is cross entropy or mean square loss, they are convex functions. So no feedback loop is needed now. And it is believed to be one of the easiest realizable quantum machine learning algorithm in NISQRC devices. Yeah, and some recent work also implement it.
Can I ask a question?
Yeah, of course.
So what's the point of the quantum system in the middle?
Yeah, so the motivation of why people marry quantum system and machine learning is because the quantum system, it has a very, very large Hilbert space. For example, as I said, if you have L qubits, now the possible output features you can obtain from this quantum system is like exponentially large. And it's due to the complexity of the quantum dynamics, such features are complicated enough. So maybe it's very hard to generate from a classical circuits or a classical physical systems. So that's why this is the main intuition behind it. Yeah,
I can use stochastic classical circuits. It will also have an exponentially large configuration space. So where is the advantage in the quantum? I mean, how do you know you have some superposition or some coherence that goes in and how can you quantify a possible advantage of the quantum circuit over stochastic classical circuit?
Yeah, I would say this is still some open question. So you may need, so for example, like some computational assumption to separate the classical and the quantum. But this is
Not even
not
that.
discussed.
I mean, even I will be very happy with even some empirical evidences that you have any advantage in this.
Oh, yeah. I think in the in this work, I think I didn't put that in the main slides, but in the backup slides, I think I showed some result that you suppose you have some randomly coupled quantum systems, and empirically you just cut off some couplings to disconnect the quantum spin network, and you can see the system with those random coupling and without those random couplings, they behave quite different, and you can see the randomly coupled one with more complicated connectivity shows a better performance. So you can think that if you cut off,
that makes sense. But
yeah,
why do you think there's anything quantum there, any quantum advantage there, in the sense that if you took this thing and you replaced it with something stochastic and classical and complicated enough that you would not get the same results or even better?
Okay, but I think this is some aspects I never numerically explored it. Yeah. But I would say sometimes if you use a quantum system instead of some classical system, it has a better, it's not discussed in this talk, but it has some better performance because suppose your output is stochastic, as I said, in the classical stochastic systems, not every feature is usable. So some features, they are too noisy to be used. So you need some metric to quantify how many features you can use from these systems. So in other work we published last year, it talks about such matrix, and we found that with such quantum entanglement or without such quantum entanglement, those metrics that quantify how many features you can use from a stochastic system is quite different, and the system with entanglement shows some better performance compared to the classical one. Yeah, so that's about about how many features you can use it. This is not discussed in this paper, but we have our group have some other works. I think I didn't put a reference here, but we have some discussion on that. So yeah, even if it's a stochasticities, but in practice, sometimes the quantum may shows a better performance, compared to to the classical analog of it. Okay.
Thanks.
Yeah, but this is a very good. Yeah. Oh, sure.
Sorry. Sorry to interrupt. Yeah, just another clarification question. So on the right box, the prediction is y equals omega times dot x. Is that done on the classical computer?
Yes, exactly. So this is this is convex optimization problem. So really, it's just done in the classical computer. Yes.
Okay, I see. Thank you.
Sure. Okay, let me move on. Okay, so such architecture of quantum reservoir computing is especially suitable for processing a task with indefinitely long input and output. So many tasks fall into this category. For example, suppose you have a physical systems. Given the drive, you want to predict the dynamics, or in some language models, you give some prompt and you need some response from these models. And as we mentioned before, because the input length has it is indefinite, so usually the encoding and the processing time is far longer than the coherence time of the quantum computer. And here is one particular example. It is a benchmarking task dating back to 2004 called the channel equalization task, which we will discuss multiple times in this talks. So let me first introduce what is the channel equalization task. So this task considers transmitted messages distorted by the linear interference and some nonlinear saturations added by some background noise. And the goal of this task is really to reconstruct the original messages y star given this distorted signals um. So yeah, that's basically the task description. And let me first introduce what a traditional quantum reservoir computing work, it really works as follows. So suppose we have the systems for the quantum system used for encoding, then the inputs are recurrently encoded into the quantum system time step by time step. Namely, the current state is determined by both the last state and the current input. And we use some quantum measurement to get some desired output values, but you may find the dilemma here, because if you measure, you just disturb the system, and all the states afterwards will be conditioned on the previous output or outcomes. Then this result some feedback or back action to the system itself. So one naive way to resolve this problem is just to run only the first time step and take many shots of measurements to get some output. And then we reinitialize it, run 2 time steps, measure, and so on. But you can see the drawbacks. It's quite obvious. We need quadratic time consumptions, O(n) squared, if we have a input length capital N. And those reinitialization prevent us from uploading the online data in a very streaming way. So to solve those questions, a very straightforward way to deal with that is that we can add some mid-circuit measurements just on the part of the qubits and leave the other qubits unmeasured. So this is the schematic describing such mid-circuit measurement. It is a little bit complicated, but let me divide into several parts to introduce them and one by one. So first of all, let's do the encoding part, where we embed the input into the same systems at each time step. And for example, we can use some Ising-type quantum spin network, which consists of error qubits that are randomly coupled to each other. And in the second part, we extract the information by measuring a subset of qubits. So in one shot, we obtain 1 bit string at each time step, for example, in the first step. Then conditioned on the measurement out bit strings, we move to the next time step. And after the evolution, we measure the second bit string. Then we can execute the whole circuits for S shots, take the average, and get a probability histogram for each time step. So they forms the output features. Finally, those output features are linearly combined to each other through the output weights. Here it is important to mention that those weights doesn't depend on the time index n. And we just need to train those output weights and fit the target value, Y star, as much as possible. So right now, everything seems to be good. We leverage the partial measurement, partial mid-circuit measurement to access the information from the quantum systems. However, our work in this paper showed that the computer will lose all its information when being monitored in this way. So after a very long time, we can check that the output does not depend on the input anymore. It just gives you some flat histograms, and it doesn't depend on the input value U or the previous history. So we call this phenomenon the thermalization or scrambling in quantum reservoir computing. We emphasize here that this always happens even if you don't have any dissipation and you manipulate everything in an error-corrected quantum computer. Those amnesiac behavior still appears when you monitor the system in this way. So this is the problem we need to resolve. And in this second part, I will introduce our solution to such thermalization problem. To analyze the dilemma between the information access and the memory persistency, we developed a mathematical tool called quantum Volterra Series, which I will briefly discuss on 2 slides afterwards. This theory can provide many solutions to the thermalization phenomenon. But here in this paper, we report the simplest one that can be realized in existing quantum computers. So such algorithm is what we call the NISQRC reservoir computing, or NISQRC for shots. And in the NISQRC, we always put deterministic reset after each measurement on the readout qubits. And we need to reinitialize those qubits after the measurement to the ground state. So this trick is also used in many other quantum computing algorithms, like the holographic simulations or some others. So if you're interested in it, I supply some reference here. And this means by taking this readout, taking the measurement and do the reset, we actually divide all the qubits into two different types, the readout qubits and the memory qubits. So for the memory qubits, we never measure them. Their function is just to store the history information from the past. And by applying the quantum Volterra series to these circuits, we can ensure that now we have a powerful machine without amnesia. It has some non-trivial behavior, even after a very long time. It won't normalize to some flat histogram. And this NISQRC scheme enables streaming online data because you don't need to restart the whole algorithm after each measurement. You just reinitialize some part of the qubits to the ground state. And the time resource is proportional to the input length m, which is quite efficient compared to the previous O(n)² time consumption. And after resolving the thermalization problem, we can move on and understand the dynamics of the NISQRC in a more detailed way. And before doing that, here are several terminologies I have to introduce when I go to our main result. And since we are talking about an input sequence and some output sequence, you can think that input and output, they are functions. So the maps between them are actually a function, and it's no longer some function, it's a functional. Then we call a function causal if the current output only depends on the past input. And we also call a function time invariant if a time delay on the input directly results in the same time delay on the output functions. So here is a particular example of time invariant functional, just to kind of with, manually. This is some functional which only depends on two steps before and the current inputs at the current time. Okay, then this is some fact that any causal and time invariant functional has such Volterra series. It is some generalization of the Taylor series, but they are defined for functionals, not for function. And in Taylor expansions, all the coefficients are given by the derivatives. So it gives you some scalars or some vectors. But here, the coefficients, it's no longer coefficients. It gives you the kernels that can be used to reproduce the functional output. So for example, let's take a look at the first term. It represents the linear contributions. So it forms a linear response. The current output is a convolutional product between a Volterra kernel H1N1 and the past input U at N minus N1. And you just take the product together and sum over them for any positive N1. So this gives you the first order linear response. And you can interpret the second order contributions in a similar way. So here, this is some classical Volterra series. But since we're talking about some quantum systems, we can generalize it to the quantum system by replacing the classical kernel with some Q number. So our main result in this paper say that asymptotically, it means after a very, very long time, after sufficiently long time, the NISQ reservoir features have this form of quantum Volterra series, where all those h hat of k can be computed by using, for example, the BCH formula. This is one example of the first and second order Volterra kernels in some system where I only output just one output features. So as a comparison, I also put the second order Volterra kernels of some biological neurons. So you can see there are some similarities here. These kernels have some decay patterns, which indicate that those natural systems always have some fading memory properties. And a more detailed analysis can quantify such observation. This formula gives the contributions from the input t time steps before the current output. So the red coefficient here only depends on the POVM, which is unimportant in this formula. And those brown terms, lambda, are the eigenvalues of a specific quantum channel called P0. This quantum channel P0 is defined by the underlying quantum reservoir, or the way you encode it. An intuitive way to understand why this is a quantum channel would look like this. So suppose you have a system, it is coupled to the environment. So initially it's in the product state, but after evolve under overall unitary evolutions, and then if you trace out environment, it will produce a quantum channel on the system part. And we can show that it is equivalent to the CPTP map, which is completely positive and trace preserving map. So due to the CPTP nature of P0, if you solve the eigenproblem of this P0, you can find that all the eigenvalues lambda of this P0 must lie inside the unit circle of the complex plane. And this largest eigenvalue, which is 1, corresponds to the fixed point of this channel. And if this channel is, for example, we are using Ising-type quantum systems with random coupling, then for such a generic Hamiltonians, we can make sure that it only has some unique fixed point in these systems. Then the final blue terms F alpha are called the internal features of the NISQRC. So these internal features are activated by the input value u p times steps before, and they decay with totally different but computable rate lambda alpha, which are the eigenvalues of CPTP map P0 we defined in the previous slides. Then as a result, we can see the memory fading rate is totally determined by the second largest eigenvalue of the quantum channel P0. And it suggests us to define a memory time of the NISQRC as the half-life time of this particular internal feature. So now it's important to know that in practice, any task should have its own relaxation time. We call it N task. So for a good quantum reservoir, if it wants to resolve some task, then it must have an appropriate memory time which fits the intrinsic dimensionality of the task itself. So one way to control the memory time is, for example, you can tune the evolution time in each time step. So here is one plot. It's a function of memory time nm as the encoding step duration tau. And you can see when you change the value of tau, the memory time can vary within a very wide range. So for example, if tau is too small, then this unitary evolution is very close to some identity. And when you after you substitute to the computation of memory time, it implies some very long memories. Okay. And after talking about so many properties about memory, we never talk about the dissipations inside a quantum system, or the memory kernels and the memory time. They are defined in the decay-less systems. But you may ask, what will happen if I put some dissipations inside a quantum system? Will the memory kernel or the memory time totally, destroyed by adding those decay or dephasing? So our results show that this may not happen if your decay rate is not tremendously large. So by adding such decay or dephasing at each time step, the overall system is not evolved only under the Hamiltonian, but also some Lindeblot equation terms. And we can simulate the Volterra kernels. For example, this is a first order kernels with zero dissipations or non-zero dissipation. And you can see that the moderate dissipation does not destroy the general shape of the quantum Volterra kernels. the same observation also is also observed to the memory time. So we can plot the memory time as a function of the T1 time of the quantum systems. If there is no decay, it gives you this black dashed line, which is the memory time is kind of non-trivial. But if we change the T1 time and also keep the evolution time tau, then you can see the memory time decays when the decay rate becomes larger and larger. However, as long as the decay rate is not so large, you can still see that at this point, the memory time is also some non-trivial values larger than 1. Okay, so it means that the memory persistency is totally controllable, not only through the Hamiltonian parameters, but also the qubit lifetime. And the persistence memory time is not necessarily bounded by the qubit lifetime.
Sorry, I have a question over here.
Oh, sure.
Yeah, the previous slide. So maybe I missed it, but what is the implications of like the kernel not being destroyed by the dissipation? Like the implications of that.
The dissipation. I'm saying that it is not destroyed. Yeah.
Yeah. What's the implication of that? Like how will it help in our task?
Sorry, could you repeat?
Yeah, because like you say, okay, now we kind of like moderate dissipation. Basically, it doesn't really kind of destroy the kernels, right? Then it's like like how this kind of observation translate into our task, like our kind of.
That's another
sure
question.
about,
I don't think that.
Not too sure about whether it's the right question to ask. Like, I'm just like wondering how this translate into the task itself. It's just like, or the accuracy wouldn't change too much, or what other things, like what other things don't really change? Because now I didn't really kind of have intuitions of how the kernel would really kind of affect the performance of the QRC or NISQRC. Yeah.
So if your output features is changed, then you use those output features because you take the linear combination of those output features to approximate some desired values. Now your kernel changes, and then the kernel changes, then it directly changes your output features, and those output features would be reflected to the output weights. So the output weight is totally different. Then it has some effect in this way, but we will see practically this change. I will show you some result. This change does not totally destroy everything. It has some moderate shift for the testing error rate, but it's not totally destroyed everything. So for example, if you remove the reset, as I said, when you encounter the thermalization, now this is a totally different story because all the kernels, the H1, H2, all the kernels, they just vanishes. They just become 0. So the only terms remaining is just the H0. Then in these situations, if all kernels vanishes, then the features it is just some trivial features, and then it doesn't work in the task. But if you just change the H1, H2 moderately, then I would say in practical, it just changed the output feature a little bit, and it also affects the output weights, but it won't fundamentally change the testing error rate. Yeah.
Right. That basically the feature extraction is stable under the dissipation, moderate dissipation. Okay, got it.
Yeah. So this not only happens for the first order features. I think I didn't put the result of the second or higher order features, but I would say even for higher order features, as long as your dissipation rate is not very, very large, then the general pattern of such kernels is minimally affected.
Right, I see.
Okay.
Got it, thanks.
Cool. Okay, I think I still have 15 minutes. So in the final part, I will introduce.
Sorry, can I just interrupt here again?
Yeah.
On the previous slide,
Sure.
you have a Markovian example, so because you're using the Lindblad equation, right? So is this a specific case of, I mean, the previous slide from this this Volterra series that you introduced is more general, has I guess it has longer memory effects, so at like N1, N2 and all that, right? So like the second order will involve more than beyond Markovian type of description, right? So I think here the only in some sense all the N2, anything beyond N2 is not captured. That there's no influence of more than one time step for the example you have. Is that correct?
That's a kind of different things, because the effective dimensionality of from the input to output, it is given by actually the memory time. So it doesn't say that. For example, you may have a very strong NM. So NM is computed from lambda 2, which is computed from this particular CPTP map. Then for example, NM is large enough, then I think both N1 and N2 would have some effect as long as both N1 and N2 are smaller than NM. So NM is actually the cutoff dimensionality, not just some dummy variable N1 and N2 here. Did I answer your question?
No, yeah, what I mean is on the physics of the actual system. If you have non-linear type of dissipation, not just a Markovian, sorry, not memory effect in the so Markovian is only like the last time step has an effect, right? So if you have something that goes longer in time with longer memory effects, then is that how is that related to the Volterra series, where the higher order terms have more influence or more importance, or it's not related? Yeah.
Okay, it's a good question. So here I would say this equation, it describes only just one step. So it means that it is a model between these two time steps. Let me go back to the verification. Yeah, it describes something like now we have if we don't have any dissipation, it gives you this perfect unitary UU1 at, for example, the first time step, or the maybe the UUN. Okay, the UUN. So it's the thing before the deterministic reset and before these steps of measurement. So this Lindblad equation is only used in this part. I'm not sure if you add those measurement and the deterministic reset, it could affect the conclusion that it's valid to use the Lindblad equations here. I do believe this is correct, but unfortunately, I didn't check it. But I hope it's still valid in each time step. Then you can fully decompose your problem into those measure and reset and the Markovian, sorry, the Lindbladian evolution inside this. There's nothing intertwined to each other between these two things. I have to say that I have never checked the joint effect if you put those measurement and reset as a part of the Markovian evolutions, but I hope that can be separated.
I think the joint one will be non-Markovian, right? Because Markovian is, as I understand it, is only related to the last time step. Or rather, you need a bigger model, something that's beyond.
But that happens inside the system. That happens inside this box. So and I would say at each time step, initially after you do the measurement, now you fully decouple the memory and readout. So you should be able to still use the Markovian just within this box.
Okay. Yeah. I think that's fine for here, but I'm just saying if there's there's a way, I guess there should be a way to generalize this to a non-Markovian version then.
Yeah, you're right. That's a very good.
So then you have more memory effects being involved or captured by this algorithm.
Yeah, I'm not sure whether in this way you can do a decompositions or some decomposition like in this way. That's something need to be checked.
Okay. Yeah. Thanks.
Okay, great. Yeah. Okay. Okay, so let me talk about the final part, which are the results of numerics and experimental implementation in the IBM quantum devices. And so, yeah. And before talking about the result, let me just give you some review, because in this talk there has already been a lot of quantities involving the time. So I just list all the notions here for clarifications. So now our messages has a total length. It is an integer, which can be indefinitely longer, and the task relaxation time in when we set up the channel equalization task, we manually set the dimensionality as to be 8. Then, as I said, we need to engineer the memory time inside the quantum reservoir such that the memory time, the intrinsic memory time of the quantum system, does fit to the number of the dimensionality of the task. And we have a total running time. So for each time step, the system is evolved for tau, and we have n different symbols. Then the total running time is n times tau. And as I said, in practice, we want to make sure that the evolution time in each time step is smaller than the T1 time. But the total running time, n tau, can be much longer than the T1 time. So that's actually very important, because eventually we want to argue that our scheme can go beyond far longer than the T1 time, even if each time step is shorter than the T1 time. But eventually the total running time can be indefinitely long. Okay, so this is the numerics done in a 6-qubit quantum reservoir, and we plot the training and the testing error rate as a function of the test message length. So you can see this is the T1 time. So you can first look at the blue lines. This is this shows the training and the testing arrows without any dissipations. And if you look at the purple lines, they're exactly the training and the testing arrows with dissipations. And you can see they don't differ too much. It means that even if you add some moderate decay, which is around like 10 times of each evolution unit, then you can still make the NISQRC algorithm work. And yeah, so I think in this plot, we process some data which has a length of 500 times of T1 time. And you can see the NISQRC still process this task with some good behavior. Okay, and by looking at these red lines where the reset operations are removed, we find that both the training and testing errors are very, very high, barely just some random guessing. In this particular examples, this random guessing only have 25% of accuracy. I mean, this is reasonable because we have already showed that the removal of this reset gives you some amnesiac system. So eventually you won't get any information from the input distorted signals. And this result just confirmed that the absence of reset exactly leads to some amnesiac system. And of course, some similar phenomenon can also be observed if we replace our NISQRC algorithm with some previous quantum reservoir computing scheme. For example, the quantum non-demolition method proposed in this paper. We plot the same simulations by using the green lines here. You can see the green lines and blue and the red lines, they actually overlap together, but it's just to say that the QRC, the reservoir thermalization still happens if you use such quantum non-demolition methods to extract the informations. And more importantly, we also
sorry, I have a question.
Sure.
In the first slide. So actually from this graph, I kind of have two questions. The first one is a bit out of scope, but I'm just like trying to see what would happen over there. Because over here you have a deterministic reset, right? Basically just like after the measurement, then you have to
this one?
Oh no. As in the plots. So you have
Oh, the plot.
yeah. So you have the without reset, which is 0.25 the error rate, and then with the reset, then you basically just like decrease the error rate by a lot, right? And this reset is basically a deterministic one. I'm just wondering, what if you have a probabilistic kind of reset? Just with probability of like p, then you reset with probability 1 minus p, then you kind of like keep feeding
Are you
forward.
talking about the measurement induced phase transition style of reset? Because that's kind of different, because that's randomly measured, not randomly reset. And
yeah. So basically,
okay,
it's still still on your scheme. Just that now, like after your measurements, like you like on the without reset one, you just like fit the post measure state into the next time set, and then just like keep doing that, right? And then with the reset one, you just like measure, and for the next time set, you kind of like reset it to be 0 state, and then just keep forward. And now, what if you have with this kind of mixed state? You have for p 0 0 plus like 1 minus p. Like, would you see kind of span like by increasing p, you're increasing the probability of resetting that? Would you see the error kind of decreasing, because there's a big gap over there, right? So I'm just wondering whether if you do this kind of probability reset, you can just like fine tune the error rate. Of course, like what we're expecting over here is that the deterministic reset you give a better result. But I'm just wondering whether there's some kind of inflection. Like for example, if there's a threshold of p that you kind of like have a reset, and then 1 minus p you like for example 0.25 or something, or maybe 0.75% of resetting that, and 0.25 keeping that. Will it kind of like keep the kind of like error rate lower than the deterministic reset one? Yeah. Just an open question. So it's kind of beyond the scope.
I get your point, because that's why my first impression is it's very close to what people talk about when people talk about the measurement induced phase transition. But that's randomly measured. That's not randomly reset. But I would say this is interesting question, because p equal to 0 and p equals to 1 seems to correspond to two different limitations of this plot. So you may expect some phase transition if it happens in this kind of probabilistic reset settings. That will be a very interesting open question. I would say, good.
Okay. Maybe we just like let you kind of like finish the talk first, and then we can just ask other questions.
Sure, of course. I think I only have just one more slide where we experimentally demonstrate that NISQRC in the 7-qubit chain of a real device. This device actually has like 27 qubits in total, but we just use 7 qubit chain to implement this. And we use like I think I use 4 memory qubits and use these 3 as a readout qubits. Then it still performs well in the channel equalization task with some streaming input of arbitrary length. And here, the previously ordered numeric simulation are done in the quantum annealer or quantum spin network Hamiltonian resolution. But in IBM quantum devices, it is gate-based. So your encoding system is slightly different from the previous one. It should be replaced by some trautorization version of the quantum Hamiltonians. And here I supplied the average T1 and T2 time of this device. It's around like 100 microseconds. However, we can successfully apply the NISQRC algorithm to the channel equalization task, which can be far longer than a coherence time. I think the longest time we choose is around like 1 milliseconds. And when you observe these purple lines, you can find that under the feasible number of shots, around like 10,000 to 100,000, it's feasible in superconducting platform. Then we found that it can reduce the noiseless classical logistic regression error rate by around like 1/2. And finally, we can check this brown dot, and it demonstrates that by remove the deterministic reset in the real quantum reservoir, would make it amnesiac. So it becomes a trivial reservoir after you remove everything, and it still gives you some error rate, which is very close to the random guessing. That's around like 75%. So it clearly showed that our online learning algorithm, NISQRC, overcomes the merriment-induced thermalizations if we add those deterministic reset. And it can run on the input signal lenses unrestricted by the qubit coherence times. So here, this is just some summary. We designed the NISQRC, which is, it's well suited to the state of art development of the experimental quantum techniques, because this architecture, we proposed it like 2 years ago, but the mid-circuit measurement and deterministic reset is just realized in November 2022. So just around 2 years ago. And a lot of platform cannot do that, but superconducting platform can do such mid-circuit measurement and reset. And we also, in this paper, we also understand the memory properties of the particular design, NISQRC, by using the theory of the quantum version of Volterra theory and the quantum channel theory. And we can define two important quantities, the memory time and the memory nodes, or the internal features of a particular NISQRC. For getting, so by getting those memory time, we can, will tune the parameters inside a quantum reservoir such that it can, you can choose a correct regime of internal parameters, randomly sample it, and make it work. And we also add the dissipations in the NISQRC algorithm, and we found that as long as this dissipation is moderate, it's quite robust to the decay or dephasing. And of course, we have some experimental demonstration when we collaborate with IBM Quantum's people. We run that in the IBM Quantum Algiers, which has a, it has the running time is far longer than the coherence time of the device itself. So yeah, before wrap up, I think I want to acknowledge my advisor, Hakan Turechi, and my collaborators in Princeton and collaborators in IBM Quantum, Nick Brown. So Said and Nick, they carry out the actual experiments in the IBM Algiers quantum devices. And I also acknowledge to Jerry, Guillaume, and Graham, who bring up the ideas of using the benchmarking task of the benchmarking task to verify, to validate, and demonstrate our ideas. I also acknowledge the funding support from the Air Force Office of Scientific Research and the Defense Advanced Research Projects Agency. And thanks for your attentions in the morning. And if you have any questions, please ask me or send me the messages through the emails. Okay.
Yeah. Thank you, Fangjun, for the very detailed and interesting talk. For the audience, if you have any questions, just unmute yourself and ask a question, or type your question in the chat, and I could help asking that. Yep, Tip, you can go ahead and ask the question.
Hey, thanks for a very interesting talk. I read the paper a few times, and now I get more insights of how the resetting helps setting the stage and help make things better. I have two questions. The first one is about the expressivity of your model. So it seems like to evaluate the expressivity of the model depends on understanding the kernel in the quantum Volterra series. Have you thought about what kind of quantum reservoir is we potentially have a higher expressivity if you look through the lens of looking at the kernel representation?
Yeah, I think this question is kind of similar to some previous audience question in the middle of the talks. So I would say sometimes in practice, a quantum system with more entanglement gives you stronger expressive ability. So you can see that now we have some backup slides. Yeah, so if you have something like the randomly coupled quantum spin networks, and you may cut off some of the connection, it gives you different connectivity, and you can see that the behavior becomes worse. And you can we define some metric to quantify the expressive ability called capacity. Such capacity quantifies how many features you can get from the quantum reservoir, and you can plot you can have a plot of the capacity as a function of the strength of those coupling. You can find that the coupling, as you change the coupling, initially all the expressive ability becomes larger and larger, but after some maximum, it reaches some maximum, but then it decreases when you use a very, very large coupling. So it just gives us some hint that you need to choose some coupling which is kind of close to some phase transition point in your model, such that it gives you a better capacity or expressive ability to maximize your ability to fit the desired target value. But right now it's more like a numerical evidence or some practical impressions. But this happens in a lot of systems, like in the Hamiltonian system or the circuit-based systems. Yeah.
Interesting. So you say that you come up with a measure of how to quantify how many features that the quantum reservoir computing can be extracted, and you say that
exactly.
Close to the phase transition points, which seems to be consistent with many proposals, including like the original Fuji and the Roberta Sambrini's group in Italy, in Spain. That show that those transition points, somehow the memory capacity and so on increases. So this kind of counting
kind of similar.
is a useful thing to do. Oh, I see. Interesting. But that's not there's no analytical prediction of why this is true yet. Is that correct?
It's not an analytical result. We just have some numerical evidence, but that's we observed this phenomenon in one of my PRX paper published last year. We have some figures talking about, as I described. You have some the metrics quantifying the features. It has some non-trivial functions when you change the coupling of the system. And you can see some maximum values at a particular J, the coupling, and you can of course quantify the mutual information or we also check some information theoretical values to see how entangled the system is. You can see the peaks the peak happens at a very close J, which maximize the capacity or the expressive ability. So this, I won't say that happens for each system, but that happens for several systems. Yeah.
I see. Oh, thanks. That's very nice. I'll take a look. And then another short question. So in all these experiments, have you looked into the case of short noises? Recently, we wrote a paper on extreme learning machine, and we showed that if you have a reservoir that is strongly entangled, like high random kind of ensembles, even though it's extremely expressive, it has exponentially large Hilbert space exploration capacity, but it can cause exponential concentration, and the output becomes input agnostic. And as a result, you get a random prediction, even though you train it quite well, because it doesn't generalize. So that causes come from the concentration of the observables, and you need to increase the number of shots exponentially large in order to make sure that you get input dependent prediction. So does any of those happen here at all? Or?
So again, I think we discussed the same question about the short noise in the same paper as I mentioned in our last year's PRX paper, because as you said, the how random circuits. So people use previously people use a metric called expressivity. It quantifies how the encoding example is close to the two design examples. So that's called expressivity, because usually people think that if the ensemble is very close to the 2 design, it has a very strong expressive ability. However, in the metric we define in our PRX paper, we can analytically compute our metrics of a 2 design or how random, not even how random, just 2 design circuits, and we can show that the capacity is actually very low. So it should be bounded just like by very small values. So it means that actually in practice, when you consider about the shot noise, this is actually a very, this is 2 design or how random is actually a very bad encoding scheme. So here, I think in this paper, we didn't use our, didn't use the result in our PRX paper, which talks about how to quantify and mitigate the shot noise. But I strongly believe that we can use that techniques. So that's called eigentest learning. If you read that papers, we just we can identify what type of features it has low noise and what else are the features with strong noise. Like we can identify such low noise components in your features. And by only just using those low noise features, we can show that you truncate the high noise part, only keep the low noise part. Of course, you need to determine how to truncate it. But once you get this truncation index, and we can see that when you can just use part of the low noise features to do the training and testing, and it can minimize the generalization error. And yeah, this is something we have already studied. Even if we didn't do that in this type of work, because in this work, everything are more complicated because first of all, we need to ensure that everything not thermalized. This is already very non-trivial thing. And I do believe that by using the same techniques, you can reduce the testing errors to some extent. Yeah.
Wow, interesting. Thank you. I'll take a look. Thanks.
Okay. I think we have enough questions for today, and we can if the audience have any more questions, like feel free to email Fangjun to ask about the questions. So thanks again the speakers for the very, very interesting talk, and yeah, see you all next time. And thanks Fangjun for sharing your work.
Yeah, thank you.
Our seminar. Yeah, see you.
Yeah.
Bye.
See you. Bye.